wanted to finish up the derivation of the uh, equations for linear regression with the augmented error function, in which we add a so-called L2 penalty on the size of the weight vector as part of regularization. So let me go to the whiteboard here. So in the first regularization video, we talked about the basic idea of regularization is to optimize something called the augmented error function, which includes the ordinary error function for whatever machine learning algorithm that you're using, plus some kind of complexity penalty. So this omega of W is some kind of complexity penalty, and different regularization schemes have different ideas of what this could be. The one that we're going to be talking about in this derivation is this. It's just the sum of the squares of the weight vectors. This is sometimes called weight decay or Tikhonov regularization. And there are other kinds too. So maybe we should just go ahead with the derivation. You know, the basic idea here is to solve the equation, the gradient of J as a function of W is equal to 0. So we solve this equation in terms of W, and then the W is the sort of optimal solution to minimizing the augmented error. All right, so it's just a gradient problem like we've done before. This is just the ordinary mean squared error function that we've seen several times here. You know, this is the predicted value in linear regression, which we sometimes call y hat n. So one way to understand what's happening here is we have, you know, the prediction minus the true value squared, and then you average those. This alpha is a free parameter, which you have to choose based on the data set that you actually have. And here's the sum of squares part. So let's get started with the derivation. So first I'm going to rewrite this initial part as 1 over n times the norm squared of xw minus y bar. So this x is the matrix whose rows are these little x's. And so this vector y is the vector of true values here. And down here is xn. Okay. And there's a square here. So let's quickly argue for why this is right. So if you take this matrix and you take its product with W, then what are you going to get? You're going to get a vector of predictions, which we could just call y hat. So this will be y0 up to yd. So this dot that gives you the initial prediction, which we could call like y hat 1, and then you get y hat 2, etc., all the way down. So this is like what we might just call y hat. So this is the vector of predictions. So that's exactly what this expression is. You take the prediction minus the truth and then square it and then sum all those up and divide by n. So these two expressions are saying the same thing. And this, we could vectorize it if we write it like alpha times wt times w. So this is saying the same thing. You know, this is just the dot product of w with itself. Okay, so all we've done here is we've rewritten J, and I want to keep going and rewrite it and still other ways that make it easy to take the gradient. So this is the same thing as 1 over n times, oops, that W is too big, W transpose X transpose minus Y transpose times XW minus y. And then we're just carrying this along for now. And so now we FOIL this part out. And so this is 1 over n. This becomes wt x to the t x w minus wt xy minus yt xw plus y transpose times y. And I'm still just carrying along alpha wt w. So two things to, well, one thing that has two parts to notice here is this is just, this is y hat transpose, and this is y hat. So both of these things here are just the dot product of w and y hat. So all of that is just 2 times w times y hat. So I'm going to combine them in that way. Not exactly in that notation. So this middle part we'll just call, this will be wt xt xw minus 2 times, how should we write this? I think like this, okay. Xy plus yty, and we're still just carrying along alpha times wtw. All right, so what now? So now we're actually ready to take the gradient. This is still just j of w. And in order to take the gradient, we're going to use this formula, which we've talked about before. So it's for a quadratic form. So A here is a square matrix. This is the same thing as A plus A transpose times W. So usually when we use this, we can assume that A is symmetric. Remember that, well, in all the cases that we're interested in, A is symmetric. And in that case, this is just 2 times A times W, because A and A transpose are the same. So we can apply this formula 2 places in this expression. One of them is here, and the other one is here. Another way to think of what that is WT times the identity matrix times W. And of course, the identity matrix is a symmetric matrix, and X transpose times X is also a symmetric matrix. So we can use this formula in those 2 places. For this part, you can think of this as just WT times some other vector B, where B is playing this role here. And remember, we also have this formula. The gradient of WT times B is just B, okay? So that takes care of almost all the gradients that we have to take here, except for this part. This is actually just a scalar because it's the dot product of W with itself, and it has nothing to, sorry, of Y with itself, and it has nothing to do with W, so it's partial with respect to every component of W is 0, so its gradient is just the 0 vector, so it basically just goes away. Okay, so now we go ahead and take the gradient. So gradient of J is, we can ignore the 1 over n and distribute over sums, just like the regular derivative. And this becomes 2 times X transpose X times W for this first part, minus 2 XY for the second part, plus 0, so that I'm just not even going to write it. For this part, we use the formula again, and this becomes alpha times 2 times W. Okay, and you can think of it as I times W, but it's the same thing as just W. All right, and now we set this equal to 0. And we want to solve for W. So let's collect all the terms that involve a W. One thing we could do immediately is cancel all these annoying 2's. So all those 2's are gone. And we can distribute the 1 over n. And we get 1 over n times x transpose x times W minus 1 over n times xy plus alpha W is equal to the 0 vector. Man, I'm already at the bottom of my screen. I'll have to start again on another page soon. So let's put these W's together. You get 1 over n xtx W. Sorry about my daughter squealing in the background if you can hear that. Plus alpha W is equal to 1 over n xy. All right, so let's copy this and take it with us to the next page. Oops. Okay, so here we were. And last time when we did this without this regularization term, the 1 over n's canceled out. Here they don't cancel out, but you can still kind of clear them and do a little cheat. So let me show you what I mean by that. So if I multiply through by n, then I get xtxw plus n alpha w is equal to xy. So if you look at the formulas for the normal equations for a regularized linear regression, which is what we're doing, instead of writing this n, they often just rewrite it as another parameter. In fact, often they don't even change the name. And we're going to do that too. But just so I'm not actually lying, I'm going to call this lambda, where this is, so lambda is equal to n times a. So it's just sorry, n times alpha. So it's just a rescaling of the regularization parameter by a factor of n. Okay. So this is x transpose xw plus lambda w. And now let's factor out those w's. And this becomes x transpose x plus lambda. And you can't just have a number there, because you can't add, this is a d plus 1 by d plus 1 matrix. So you have to, you can't, there's no notion of adding a scalar to that, but we can, if we factor out w, we can replace it by I, and then this really is the same. And this is equal to xy. Now we want to solve for w, so we just multiply both sides by the inverse of this, which is x transpose x plus lambda I inverse times xy. Right, and this is the formula for regularized linear regression. And that's all. So I'm going to stop the share and go back and stop the video.